The alternative to sorting is to use hashing. What is the idea behind hashing? Well, the motivation is that many times we don't really require order, we just require things that are equal to be together. For example, removing duplicates doesn't require that things to be ordered. Simply that all the duplicates have to come together in batches, but the order across duplicate batches doesn't really matter. Similarly, for forming groups in aggregation, we only need the elements of each group together, but we don't need the groups to be in any particular order. So in a sense, we are just rendezvousing the matches in time and space, but we are not concerned with what order the values come out. So hashing does exactly this. The question, however, is how do we do it out of core? In other words, how do we do it for datasets that are larger than memory? Traditionally, hashing is done using hash tables in RAM, as you learned in lower division courses. So we need to come up with a scheme for out-of-core hashing. So let's design a divide and conquer algorithm for doing this. In the first phase, divide, we are going to use a streaming algorithm, as we learned about at the beginning of this lecture, to partition data into what we call spill partitions. We are going to use a hash function, h sub p. We stream records through h sub p into disk partitions where all the matches of a single value will end up in the same partition. Since multiple records can have the same value, each partition will contain a mix of values. But for now, we only need two values that are the same to be in the same partition. As I said, this is a streaming algorithm. So when we run out of space to hold the records in memory for a partition, we will just spill the full partition to the disk by writing them out from the output buffers. So let's see an example. We start by reading each page of the original relation from disk into memory. And we apply our hash function, h sub p, to each of the records in the page to determine which of the b-1 output buffers the record should go to. For example, say each data page can hold 3 records max, and the first page contains 3 records, 1, 2, and 3. h sub p might put the first record, 1, in the first partition, while it might put the 2 record to the second one. Now the record number 3 might be put in the same partition as the first record, and the same process continues with the second page, which might contain 2 records. Our hash function might put the 5 record to yet a third partition, while the 1 record is put again into the first partition. 2 things are of note here. First, because the 1 records appear in different data pages, they are actually not stored consecutively on the disk, even though they both belong to the same partition. Second, notice that after partitioning, we ended up with 3 data pages on the disk, while the original relation only used 2 pages. This is because we need at least 1 page to store each partition, and our hash function created partitions that are more than the number of pages used to store the original relation. Needing more pages to store the output relation after partitioning will be important later on when we compute the I/O cost of our algorithm. But now let's go on and talk about the second conquer phase. How do we deal with the non-consecutive values problem that I talked to you about on the previous slide? Well, this is where the conquer phase comes in. In the conquer phase, we will rehash the partitions that we have divided up, so we are going to read each partition back into memory and create an in-memory hash table, 1 partition at a time. This time, we are going to use a different hash function, namely h sub r, that is independent of h sub p. As we read tuples in from a partition, we are going to build an in-memory RAM-based hash table based on h sub p, just like our traditional hash table that you learned about in your lower division courses. Each bucket in this hash table is just going to have a few distinct values since we are processing only one partition at a time. Once this hash table is built and sitting in memory, we'll go through it bucket by bucket, reading out the values in the individual buckets and writing them out to the disk, and making sure that within a bucket, duplicate values are contiguous. That is now easy because each bucket is very small and is already in memory. The hash function ensures that two items with the same value are in the same bucket, and we can run an in-memory sort algorithm to ensure that values that should go together will end up contiguously in each bucket and subsequently on the disk. So now let's look at an example of the conquer phase. In the conquer phase, we take our scratched disk, which we now have on the left side of the picture, created from the divide phase, and we read in one partition at a time into memory, forming a RAM-based hash table. So as we read in the pages of the partition, we run a hash function, h sub r, on each tuple, and to fill in this in-memory hash table. We assume for the moment that the hash table is no bigger than B pages. If it is actually bigger, we will have to do something special, which I'll show you in a few slides. But for now, let's assume it's no bigger than B pages. We generate that hash table, and then we walk the hash table bucket by bucket, reading out the contents of the bucket and writing them to the disk, making sure that the same values are all contiguous on the disk. Remember, in the first phase, we ensured that all values that are the same are actually in the same partition. And now in this phase, in the hash table, we can guarantee that all values that are the same are in the same bucket. So this is actually a correct algorithm. As we write out these buckets, we know that all values that are the same are now contiguous on the disk. Using the example from before, after the divide phase, we have three partitions on the disk. We read each of these partitions one at a time, applying h sub r to create an in-memory hash table, such as the one that you are seeing here on the screen. And after we're done, we simply write out each of these buckets to the disk. As you can see, all values that are the same are now contiguous on the disk. So, what is the cost of this algorithm? In the first phase, we read the entire input as we stream it through memory, and we write out the output back to the disk. So that is n IOs to read and approximately n IOs to write for the first phase. Why do I say only approximately n IOs to write? Well, because in the divide phase, we might end up with more than n pages, as I said in a few slides earlier. So the write cost can actually be more than n IOs. To get the exact cost, we need to know the size of each partition. And the notes actually go into this with further detail. But for now, let's say it's roughly n IOs for write, making the divide phase total cost to be roughly 2n IOs. What about the conquer phase? Well, we need again approximately n IOs to read the partitions back into memory. And again, approximate because we need to know the exact number and the size of the partitions in order to get that exact number. And now, assuming each partition fits in memory in the second divide phase, we will again incur approximately n IOs to write out all the buckets back to the disk. This makes the cost of the conquer phase also roughly 2n IOs, bringing the total cost of the algorithm to be 4n IOs for a two-phase external hashing algorithm, assuming again that the data starts on the disk in the beginning and is written completely to the disk at the end. As we did before, we can ask the memory requirement question. How big of a table can we hash in just these two passes? Let's think about this. In the first phase, we generate B-1 partitions. And in the second phase, we need to ensure that each partition is no more than B pages in size. So if we are very efficient with our use of memory, we can get this to work on a file of size up to b times b minus 1, or roughly b squared. In other words, we can hash a table of size n pages in about square root of n space. Note that this assumes that every hash function is about the same size, which is to say that the hash function distributes records evenly. That may or may not be true in actual practice. If we have a bigger table, or if one of our partitions is larger than b pages, because of the hash function does not distribute records evenly, then we actually need to do what is known as recursive partitioning. Let's see how that works next.